Good afternoon, Kamaljeet. So, am I audible clearly? Okay, so let's start. Yeah, good afternoon, everyone. Myself Moma Samanto, and this is your week 5 live tutorial session for the course, a basic course in number theory. So, and the course instructor is Professor Sripad Garg from IIT Bombay. So, before solving some related problems to the topics of week 5, I will ask first if you have any particular doubt from the lectures or from any assignment questions. Then I would like to solve those first. After that, we will solve some problems related to the topics. So, anyone has any problem from the theory or from the lectures of week 5? If no, then you can just say or type no. Hello, Kamaljeet, do you have any particular doubt?
Yes, ma'am, I have a doubt in assignment number 4.
Okay, so anyone else? If you have doubt, then I will ask you just after asking to Kamaljeet. So, can you tell me the your doubt?
Yes, ma'am, in question number 10.
So, can you tell me the question?
Yes, for which of the following four tuples
For which of the following tuples
following four tuples of integers like A, B, C, D, this is four tuple. Do we have a solution to the system of simultaneous linear congruences? Congruences are n is congruent to A mod 2,
Yeah, what are the linear congruences?
yes, n is congruent to A mod 2,
N is congruent to
A mod 2.
okay. Hmm.
Second one is n is congruent to B mod 5. Third one is n is congruent to C mod 6. And the fourth one is n is congruent to D mod 15.
Okay.
The options are given. First one is 0, 3, 2, 8. First four tuple.
0,
3, 2, 8, 8. Second option is 1, 3, 1, 13. Third one is 0, 3, 0, 3. Fourth is 1, 3, 5, 8. And the fifth one is 0, 3, 4, 13.
yeah. So
The last one is 1, 2, 3, 3. Actually, ma'am, answer has been released in assignment 4. I don't understand how to approach such type of question. A similar type of question in question number 9 also. But please explain how
so
we can have such type of question.
So particularly you want to know how to solve this kind of question, not only this, for question 9 also, right?
Yes, yes, ma'am.
Okay, so one thing you can check is you can just since the options are given, then you can just try to put these answers in each of these linear congruences, and you can find whether these four linear congruences are um, satisfied by any of those tuples. So for example, if you take the first option 0 3 2 8, you can see you are taking a equals to 0, b equals to 3, c equals to 2 and d equals to 8. For this one, see, n is congruent to 0 mod 2, n is congruent, okay, sorry, no, no, sorry, let me just think think for some time. We have the solutions of
Ma'am, in this way, by hit and trial, and it is very difficult to find an
yeah.
such type of.
Yeah, just let me just think for some minutes and I will just tell you. So see here, first equation is mod 2, then mod 5, then mod 6 and then mod 15. Now you can see, since I think in this way we can approach. See, for if you take the first equation and third equation, what do you see? I mean, something you can conclude from first and third linear congruences. First congruence is n congruent to a mod 2, and third congruence was n congruent to c mod 6, right? Now 6 equals to 3 into 2. So from here,
Yes,
what can you say? So
ma'am. We can say n is congruent to c mod 2 and n is congruent to c mod 3.
right. So let me write it here. n is congruent to a mod 2 and n is congruent to c mod 6. So from here, from this third linear congruences, we can say n is congruent to c, 6 equals to 2 into 3, so congruent to c mod 2, and n is congruent to c mod 3. Now, so n is congruent to both a and c mod 2, right? So from here, what can you conclude? So n is congruent to a and n is congruent to c mod 2. So their difference will also be congruent to their difference will be congruent to 0 mod 2. So n is congruent to a and n is also congruent to c mod 2. So that will give you a and c are congruent under mod 2, right? Now From similarly from this equation, from this equation and this equation, and also from this equation and this equation, what can you conclude? In the similar way, what we have done for this and this.
Ma'am, for last equation we can write n is congruent to d mod 3 and congruent to d mod 5, and we can solve similarly.
So then from from last equation, then what you are saying, from the last congruence, n is congruent to d mod 15, that will give you n is congruent to d mod 3 and n is congruent to d mod 5, right? So now you can see from here you can conclude n is congruent to c mod 3 mod 2, and from here n is congruent to d mod 3 or mod 5, and from from these two we can say b is congruent from this equation and this equation, this one we can conclude b is congruent to d mod 5. So just number it 1, 2, 3 and 4. So from 1 and 3, 1 and 3 implies a congruent to c mod 2, and 2 and 4 implies b congruent to d mod 5, b congruent to d mod 5. Now 3 and 4, this will imply c congruent to d mod 3. So now we have this one another is this one, a congruent to c mod 2. So now we know the relation between a, b, c and d. So now it is easier to check with those options, right?
Yes, ma'am, yes. Now we can check.
So you got it, right? I actually don't know what will be the solution, but I hope in this way we can proceed.
Okay, ma'am. Okay, thank you.
Okay. Anyone else? Then Moji, do you have any doubt?
Yes, ma'am. This problem boss can solve, ma'am.
So you also had that same doubt, right?
Yes, ma'am. 9th one also, ma'am.
Okay, so now you can now you can solve by yourself, right? Because it is very similar to question number 10.
Yes, ma'am.
Or do you okay, I hope you can try by yourself. Anyone else? So if no, from lectures, have you seen all the lectures? So let's since no one of you has any problem, let's solve some chosen problem from okay. So what was the topics covered in throughout the lecture week 5? So it contains Wilson's theorem, and then Fermat's little theorem, Lagrange's theorem for Lagrange's theorem, which says about the solution of degree d polynomial in Zp for some prime p, and then Euler's phi function, and so that's all. So we will so today's the problems I have chosen will cover only so I will try to solve some questions which related to which will in which we will use the Wilson's theorem, and then Fermat's. Okay. Fermat's little theorem, and next I will do some problems with Euler's phi function. So mainly these three topics will be covered in our questions. So first let's start with question number 1. Show that for a prime p and an integer a, p divides a power p plus p minus 1 factorial times a, and p divides p minus 1 factorial a power p plus a. So what it is asking, given p is a prime number and a is an integer, no condition is given on a, then it is asking to show p divides a power p plus p minus 1 factorial times a, and also p divides p minus 1 factorial times a power p plus a. So what are the as I said, I will try to cover these three topics. So we can use the Wilson's theorem and also Fermat's little theorem to show that this statement holds. So can anyone try to solve this one by yourself, or you can tell me right now, then I will try to solve. Will anyone try? For let's say for this one, so first we want to show p divides a power p plus p minus 1 factorial times a. So I would also like to recall the Wilson's theorem and Fermat's little theorem. So what Wilson's theorem is saying? Wilson's theorem says that for a prime p, p minus 1 factorial is congruent to minus 1 mod p, and this is Wilson's theorem. And what Fermat's little theorem is? it says a okay, for a prime p and for a prime p and a belongs to z, p power a power p minus 1, this is congruent to 1 mod. Okay, so using these two theorem we can show the given statements. So can anyone tell me how should we proceed? So it is asking to show p divides p minus 1 factorial times a power p. Now p divides a power p plus p minus 1 factorial times a. Now from which theorem should I use to get a power p congruent to something mod p? This is Fermat's little theorem, because it is saying for any integer a we can have this one a power p minus 1, this is congruent to 1 mod p. So anyone? Okay, so let's solve it by ourselves.
In Fermat's theorem,
Yeah, so tell me.
is there any connection between P and A?
In Fermat's theorem, yeah, what
For
is
any prime P and any integer A, or what is it? P does not divide A, is there?
that is a is not 0 in ZP. I mean, yeah, a is not equals to 0. Yes, that is the condition. That means a is not congruent to 0 mod p. This is the condition. So to show this statement, if say here in this question no condition on a is given. Now if you first take a is congruent to 0 mod p, that means p is dividing a. In that case p divides a power p, also p divides p minus 1 factorial times a. So when p is dividing a, we have this statement. Also since p is dividing a, dividing this term and dividing this term, so p is dividing this term also. Now if p is not congruent to 0 mod p, in that case what can we say? So case 1 is p a congruent to 0 mod p, then p divides a power p and p divides p minus 1 factorial times a. Thus p divides a power p plus p minus 1 factorial times a. So in this case we don't have any problem. But when a is case 2, when a is not congruent to 0 mod p, that means that is a not equals to 0 in ZP. It means this statement has the similar meaning with this. So what in this case what we can say? So by what was the Fermat's little theorem? A power p minus 1, this will be congruent to 1 mod p. So by Fermat's little theorem, what we can say? A power p minus 1 congruent to 1 mod p. What does it mean? Multiply both sides by a, then you will get a power p congruent to a mod p. Hence, now look at this right hand side. It is a power p plus p minus 1 factorial times a. So this term is congruent to a mod p. Now we need to check this term congruent to what. Now we also have seen that in this Fermat's little theorem, it is saying p minus 1 factorial is congruent to minus 1. So p minus 1 factorial times a, this will be congruent to minus a mod p. So now by Wilson's theorem, p minus 1 factorial congruent to minus 1 mod p, this will imply p minus 1 factorial times a, this is congruent to minus a mod p. Now say this is star and this is double star. Thus by these two equations, star and double star, what can we conclude? We conclude a power p plus p minus 1 factorial times a, this will be congruent to a minus a mod p, that is this is congruent to 0 mod p. So hence we can say p divides a power p plus p minus 1 factorial times a. So is it clear how to use this? This is the straightforward use of these two theorems, Fermat's little theorem and Wilson's theorem. In the similar way, we can show the second statements also. So can anyone now tell me how to solve the second statement? So second statement is asking to show p divides p minus 1 a power p factorial times a power p, no, plus a. A power p plus a. Now so by star and double star, now we can say by star and this double star, these two statement or equation, we can say p minus 1 factorial a power p, this is congruent to p minus 1 factorial is congruent to minus 1 and a power p is congruent to a. So this is congruent to minus a mod p. Thus p minus 1 factorial a power p, this is plus a, this is congruent to 0 mod p. So hence we have the second statement, that is p divides p minus 1 factorial a power p plus. So this was nothing but straightforward use of these two theorems, Fermat's little theorem and Wilson's theorem. Now let us solve another question. So any doubt in this question? So in this question it is given that let P be a prime of the form P equals to 4k plus 3. Then it is asking so that either p minus 1 by 2 factorial, this is congruent to 1 mod p, or p minus 1 by 2 factorial congruent to minus 1 mod p. So how to solve this problem? So given that p equals to 4k plus 3, therefore what will be p minus 1 by 2 factorial? So p minus 1 by 2, this term will be 4k plus 3 by minus 1 by 2, that is 2k plus 1. So n is an so p minus 1 by 2, this is an odd integer. With the form of p, we are getting p minus 1 by 2, this is again an integer, but this is an odd integer. Therefore now what we have to show? We have to show p minus 1 by 2 factorial. Suppose we are considering let m be the integer p minus 1 by 2, then m equals to 2k plus 1. So this is an odd integer. Now what we have to show? We have to show p minus 1 by 2, this factorial, either it will be congruent to 1 or minus 1. So let's see what is the term p minus 1 by 2 factorial looks like. So p minus 1 by 2, we are considering it m. So m factorial will be, actually what we have to show? We have to show m factorial. M means we have taken m equals to p minus 1 by 2. This m factorial is congruent to either 1 or minus 1. So we can write in this way also, plus minus 1 mod p. Now what is m factorial? M factorial equals to 1 into 2 into m means p minus 1 by 2. So m factorial means this. Now we have the given only what we have. We are given p is a prime. This is the only given condition, and from the form of p, that is p has the form 4k plus 3, we are just getting that the integer p minus 1 by 2, this is an odd integer. So now since p is a prime, it is given, we can use the Wilson's theorem here. So since p is a prime, by Wilson's theorem, we have p minus 1 this factorial is congruent to minus 1 mod p. This is by Wilson's theorem we have. Now let's try to relate p minus 1 factorial and and m factorial, that means p minus 1 by 2 factorial. Now what we have, what are the integers we have in this factorial p minus 1? P minus 1 factorial, this contains, this is the product of 1 into 2 into 3 up to, there is somewhere p minus 1 by 2 in the middle, into p minus 1 by 2 plus 1 up to p minus 1. Now see how many integers are here and how many integers are here. How many integers are there in this, 1 up to p minus 1 by 2? These are exactly p minus 1 by too many integers. Also see these from p minus 1 by 2 plus 1 up to p minus 1, these are also p minus 1 by 2 in number. Now what to something beautiful is here is that if you take p minus 1, just go in this reverse direction from p minus 1 to p minus 1 by 2 plus 1 and see under congruent module, under modulo p, which p minus 1 is congruent to which integer, or up to p minus 1 by 2 plus 1, these are congruent to which integer. First say p minus 1, this is congruent to minus 1 mod p. Then take p minus 2, this is congruent to minus 2 mod p. In this way, if you take p minus 3 also, you will get minus 3 mod p. In the similar way, so we will go up to p minus 1 by 2 plus 1, means up to this term. So p minus 1 by 2 plus 1, this term is exactly, we can write this term as p minus, so this is actually equals to p plus 1 by 2. Now we can write p plus 1 by 2 in this way, p minus 1 by 2. We can write p plus 1 by 2 in this way. Now see, if we take modulo p, then we will get p minus 1 by 2 plus 1, that means this last term, this is congruent to just minus p minus 1 by 2 under modulo p. So what we are exactly trying to see, so where in this term, so just write p minus 1 factorial in the reverse way, that is p minus 1, p minus 2 up to somewhere in the middle, p minus 1 by 2 plus 1, then into p minus 1 by 2 into up to dot dot up to 3 into 2 into 1, in this way, in the reverse direction we are writing. Now combine, pair these two things, p minus 1 with 1, p minus 2 with 2, and p minus 3 with 3 up to p minus 1 by 2 plus 1 with p minus 1 by 2. Since there are even numbers in the factorial p minus 1, we can take p minus 1 by too many pairs, and we are finding that from this table, what we are finding that each term from this set, it is congruent to minus 1 times each term to this set. Sorry, this is wrong pair. So each term from this set, this up to p minus 1 up to p minus 1 by 2 plus 1, each term in this set is congruent to minus 1 times some term in these pairs from here to here, p minus 1 by 2 factor 2 up to 3, 2 and 1. So we are get what then p minus 1 factorial, it will be congruent to, say first p minus 1 that was congruent to minus 1, p minus 2 was congruent to minus 2, p minus 3 congruent to minus 3, then p minus 1 by 2 plus 1, to which it is congruent to, it is congruent to minus p minus 1 by 2. So we are getting up to this term, what we are getting it is congruent to minus p minus 1 by 2, congruent to this. And also we have with the second term, I mean p minus 1 by 2, write them as it is up to 3 into 2 into 1. So in this set and in this set all elements are same, but here in this set the elements are minus 1 times elements of this set. So how many minus 1 will be there in this set? Exactly, since there are p minus 1 by 2 many elements, so exactly it will give us minus 1 power p minus 1 by 2, right? So we can since we have already taken m to be the integer p minus 1 by 2, we can write it as minus 1 whole power m p minus 1 by 2 factorial, then its square, because p minus 1 by 2 factorial, 1 p minus 1 by 2 factorial, this is coming from this set with minus 1 power m, and another p minus 1 by 2 factorial is coming from these sets. So therefore what we can say, we can conclude, so this is congruent to, implies p minus 1 factorial is congruent to minus 1 whole power m times, we can write it as p also, m also, m factorial square. So from now, using Fermat's Wilson's theorem, what we have? We have p minus 1 factorial is congruent to minus 1. Therefore, okay, before that let's see that m is an odd integer, because what we have already seen, since p has the form 4k plus 3, we have p minus 1 by 2 was 2k plus 1. So 2k plus 1 is an odd integer, that is m is an odd integer. So minus 1 power m, it will give you minus 1 exactly. So p minus 1 factorial is congruent to minus m factorial square. So now by this left hand side, this is congruent to minus 1 mod p by Fermat's theorem. Therefore this is by Wilson's theorem. Wilson's theorem. Hence what we get? We get m factorial square. This is congruent to this is minus, it will be cancelled. Then m factorial square, this is congruent to 1 mod p. Hence we have m factorial, that is p minus 1 by 2 factorial, this is congruent to plus minus 1 mod p. So exactly what we have shown, we have shown that by the form of p, since p was 4k plus 3, we have in this factorial p minus 1, in this factorial we have even number of terms, right? It is odd, therefore p is odd, therefore p minus 1 factorial will contain even number of terms. Now we are clumping, we are taking the pair, it was 1 into 2 into 3 up to somewhere in the middle, p minus 2 up to p minus 1. So we are taking these pairs, 1 p minus 1, 2 p minus 2, 3 p minus 3 up to p minus 1 by 2 and p minus 1 by 2 plus 1, that is this term is equals to p plus 1 by 2. So in each pair, so these are pairs A, B, this is the set of pairs, this we are calling it G. If AB belongs to G, then B is congruent to minus A mod P. This is exactly we have done. Now how many elements, how many pairs are there in this set G? That is cardinality of G, this is equals to p minus 1 by 2. This is an odd integer, so hence if we take the product of first tuple from each of those pairs in G, we get p minus 1 by 2 factorial. This is exactly congruent to take the product of the second term from each of the tuples in G, then what you will get? You will get p plus 1 by 2 into p, so what was the into p plus, or you can write it in this way, p minus 1 by 2 plus 1 into p minus 1 by 2 plus 2 up to p minus 2 into p minus 1. These are the all term in the second these are the all term which occurs in the second term of the set G. Therefore we are getting this product, this is congruent to minus 1 whole power p minus 1 by 2 into 1 into 2 into 3 up to p minus 1 by 2. This is exactly what we have seen now. So therefore if we take so this is exactly equals to minus 1. Since p minus 1 by 2 is an odd integer, we are getting this term to be minus p minus 1 by 2 factorial. Therefore p minus 1 factorial, this will give you, so how do we get p minus 1 factorial? Just multiply 1 up to p minus 1 by 2 with this product, then we will get p minus 1 factorial, and then we will get, so what we are taking, another p minus 1 by 2 factorial we are multiplying in the left hand side. So therefore it will give you minus p minus 1 by 2 factorial square of this term. And now by using Wilson's theorem, we conclude this term is congruent to minus 1 mod p, therefore this term will also be congruent to minus 1 mod p. Now this term congruent to minus 1 mod p means p minus 1 by 2 factorial square this term is congruent to 1 mod p, and hence if you take p minus 1 by 2, it will either congruent to 1 or congruent to minus 1 mod p. So this was the proof of the so therefore we got this one. Now next try to solve another question. Third question is, prove that an integer n greater than 1 is a prime if and only if n minus 2 factorial this is congruent to 1 mod n. So it is saying that an integer n greater than 1, that will be a prime if and only if n minus 2 factorial this is congruent to 1 mod n. So can anyone tell me any direction which I think this direction will be easy. So let n be a prime. So if direction, that means let n be a prime. What we have to show? We have to show, that means want to show n minus 2 factorial this is congruent to 1 mod n. So why I am saying this direction will be easy? Because for a prime n we know Wilson's theorem. So can anyone tell me how to proceed with that? Kamaljeet, Mothu or Denmoji, anyone? This is the easy part, easy direction.
Ma'am, we can think like y Wilson's theorem p minus 1 factorial is congruent to minus 1 mod p, and then we can open factorial p minus 1 into p minus 2 factorial.
Yeah, you are right. So you are saying by Wilson's theorem, what we get? By Wilson's theorem,
p minus 1 factorial is congruent to minus 1 mod
it
p.
is given n, so n minus 1 factorial this is congruent to minus 1 mod n.
Now open the factorial n minus 1 into n minus 2 factorial.
So this will be congruent to minus 1 mod n. Now
And
just further calculate the left hand side. What will you get? So if you calculate it is product of n minus 1 in and n minus 2 factorial. So multiply n minus 2 factorial with n and then take minus n minus 2 factorial. Just further calculation, n into n minus 2 factorial and another minus n minus 2 factorial. This is left hand side and this is congruent to minus 1 mod n. Now this term is congruent to what? Under mod n?
0, 0.
And this term is congruent to minus 1
Minus n minus
or
2.
minus n minus 2 factorial. So what will we get then? We are getting minus n minus 2 factorial. This is congruent to minus 1 mod n, and multiplying both sides by minus 1 we will get n minus 2 factorial. This is congruent to 1 mod. So this is just application of Wilson's theorem. So we are we have this term. This is congruent to 1 mod n. Now to show the reverse direction, what we can conclude, this reverse direction is something tricky. So what we have to assume here, let n minus 2 factorial is congruent to 1 mod n. What we have to show? Want to show n is a prime. So in this kind of question, so how can we show that a number is a prime? Either 1 and n is the only divisor. I mean, we have to find the set of all divisors of n to show that in the direction to show that n is a prime. But this is much complicated to find all the divisors of n from the given from this condition, one condition only. So in this kind of question, what we do, we use the method of contradiction. So method of contradiction means, first assume that P is not a prime, then we can see whether we are getting some contradiction to this given fact. Okay, so what we will do here, because this is much easier than finding all the divisors of n. Okay, so suppose n is a composite number. So n is a composite number, that means n equals to a times b for some a b belongs to 1 up to n minus 1, or 1 up to n you can write first. Now see, since n is a composite number, neither of a and b can be 1 or n, because composite number means n is product of two integers which are not equals to 1 or n. So we can eliminate 1 and n from this set, and we can write it ab belongs to the set 2 up to n minus 1. Okay. Now another, so since a is a composite number, we just take the set consisting of the integers 2 up to n minus 1 where a b lie. Now another thing to notice, if any one of a b, whether any one of a or b can be n minus 1 or not. I mean, my question is, can we take a or b to be n minus 1 when n equals to ab is a composite number? So can we take n to n a or b to be n minus 1? So if we take without loss of generality, say a equals to n minus 1, then what will we get? If a equals to n minus 1, that will imply a, since n equals to ab, a divides n implies since a divides n, so and a equals to n minus 1 implies n minus 1, this will divide n. Now we have n minus n minus 1, this is equals to 1. What can we say about GCD of n and n minus 1? So from these expression,
It will be 1.
GCD is 1.
Yes, because two consecutive integers are
Yeah,
there.
in that direction also, or I was writing by this form, what I mean that a alpha plus b beta equals to 1, that will give us GCD of a and b, this is 1. So you are also right, any two consecutive integers have GCD 1. So what we can say is that, but GCD of n minus 1, this is 1, so n minus 1 cannot divide n, thus neither a nor b can be n minus 1. Thus where if n is a times b, where ab lies, thus n equals to ab gives a b lies in the set 2 up to n minus 2, right? Now here also, now we have this condition, this is the condition, after assuming n to be a composite number, we are getting this one only. Now what is our aim? Our aim to find some contradiction to the hypothesis, means this was the given condition to show the reverse direction. So anyhow we have to get some contradiction to this fact. So for that, now let's see what happens. So here we may consider a can be equals to b when n is a composite number. Also a cannot be equals to b. These are two possible cases. So we are dividing this in these two cases. Case 1, this is a not equals to b. So some by the law of trichotomy, either a less than b or b less than a, say a less than b. Okay. Now since a and b both belongs to this set and a less than b, can we say divisibility of n and n minus 2 factorial? So a is one of the integers in this set, 2 up to n minus 2, set consisting of 2 up to n minus 2. b is also another integer different from a in this set consisting of 2 up to n minus 2. So can we say a divides n minus 2 factorial and b also divides n minus 2 factorial? Can we say that? because there are some integer from this set 2 up to n minus 2. Since a not equals to b, I mean a and b are distinct, so both of them, I mean both of a and b appears in the product 2 up to n minus 2, that means n minus 2 factorial. So since a less than b and since this means 2 less equals to a strictly less than b without loss of generality, 2 less equals to a less than b less equals to n minus 2, we have a times b, this divides 2 into 3 into 4 into up to n minus 2, that means ab divides n minus 2 factorial, that means n equals to ab, so n divides n minus 2 factorial. So from here, can you see any contradiction to the hypothesis? That means any contradiction to this fact? So what does it
Ma'am, here is remainder 0, 1 and divides n minus 2 factorial. But there will be 1 when we divide n by n minus 2.
This condition means n minus 2 factorial is congruent to 0 mod n, right?
Yes. Mhm.
But our hypothesis was n minus 2 factorial congruent to 1 mod n. Thus, this is the contradiction. So, this is a contradiction. Hence, what we have assumed is false. So, hence, in this case, what was that? Hence, in this case, n is a prime. So, what we assumed that was false? We assumed that n is a composite number. So, in this case, the n is not a composite number, that means n is a prime. Now, what is the case left? In this case, we are considering a is not equals to b. So, another case left is, that means case 2, what we have to consider here? A equals to, let a let n equals to ab and a a equals to b, that is n equals to a square. So now we are considering n to be a composite number of the form a square for some integer a belongs to which set? 2, 3 up to n minus 2. So in the very first we have seen that a cannot be n minus 1. So a will lie from inside the set consisting of 2, 3 up to n minus 2. Therefore, now here see, so take the lowest case, I mean when a is 2. Let's see what happens. When a equals to 2, that means n equals to 4, then what is n minus 2 factorial? 4 minus 2 factorial, that means 2 factorial, that is 2. Now, is 2 congruent to 1 mod 4? No, right? So, this is I mean n minus 2 factorial congruent to 2 mod, it was mod n, so we have to consider mod 4 here. So but in our hypothesis it was given n minus 2 factorial has to be congruent to 1. So this is again a contradiction. So thus n cannot be 4. Now let a is, so in this case we were taking the smallest possible case of a such that n has the form n equals to a square. Now take why we are consider actually this is the proof I have done. You may have some different way to show to prove this question, but what you will see, when a greater equals to 3, then the procedure we are or the method we are following to show n cannot be a composite number, this method will not work if you take n equals to 4. Therefore explicitly I have shown the case n equals to 4 here, and from a greater equals to 3, I mean if n equals to 9 or 16, in this case, in these many cases, we will consider some method. Now let's see what is that method. Now let a greater equals to 3 and n equals to a square. In this case let's see if we can find some contradiction to the hypothesis. So case 2 also have two part, when a equals to 2 and when a greater equals to 3. So n a greater equals to 3 and n equals to a square. Now n minus 2 factorial consists of which term? Where a belongs? A belongs to so greater equals to 3, so we can write 3 up to n minus 2, right? So a belongs to this set, 3 up to n minus 2. Now so since a belongs to this set, a divides n minus 2 factorial. Now can we find some different integer in this set such that that integer will also divide n minus 2 factorial? Can we consider some other element rather than a in this set consisting of integers 3 up to n minus 2 such that that integer will divide n minus 2 factorial? Can we find?
Ma'am, n minus 2 itself will divide n minus 2 factorial.
Yes, n minus 2 always divide n minus 2. So what we are trying to show? We are trying to show oh no, what we are trying to show here, we are trying to find a contradiction to this fact. So n minus 2 factorial is congruent to cannot be congruent to 1 if we assume this condition. Now so in this case, like case 1 means here when a not equals to b, we were trying to show n is dividing n minus 2 factorial. So what I said is a little bit wrong. If we consider a greater equals to 3 and n has the form a square, can we find another integer in this set rather than 1 such that that integer is dividing such that we can show n is dividing n minus 2. That means we want to find, I should write, we want to find some integer, let's say m not equals to a, such that a times m divides so m should be we should get m in terms of the integer a. Actually my final aim is to show a square divides n minus 2 factorial. This is my final aim. So we want to find such m such that if we product it with a, that will exactly give us in a square some condition a square is dividing n minus 2, not exactly the integer n minus 2 I am asking for. So I think I should tell it more clearly. So what is my aim is, final aim is to show n minus 2 factorial cannot be congruent to 1 mod n. So in this approach we are trying to show that n is actually dividing n minus 2 factorial. That means n minus 2 factorial is congruent to 0 mod n. Now if we find some another integer in this set which is not equals to a, and if we can show that a times m, this is dividing n minus 2 and n is dividing, we simultaneously want these two division, n that divides am and am that divides n minus 2 factorial. These are the two simultaneous division we expect from some integer in this set which is not equals to a. So the integer you have said that is n minus 2, but if you multiply it with n minus 2 with a, can you conclude anyhow that n is dividing n minus 2 factorial? You may show that, but that will be much more complicated. And if we can find some term, let's check this particular element 2a. Can you show that 2a lies 2a belongs to, obviously a not equals to 2a, and 2a belongs to 3 up to n minus 2 in this set. If you can show this statement, what conclusions you may get? You may get 2a times a that divides n minus 2 factorial, and this will imply this term is 2a square. 2a square means 2n. Now n divides 2n and 2n divides n minus 2 factorial. If you show that 2a belongs to this set, what you can conclude? Then you can conclude n divides 2n and 2n divides n minus 2 factorial. So both will imply n divides n minus 2 factorial. Now if n divides n minus 2 factorial, then you can conclude this is congruent to 0 mod n. So this is a contradiction, this will be a contradiction to our hypothesis. But before that, what is the gap here? Here first we have to show this 2a this element will also belong to this set. So if you can remember, we have done one problem in third or fourth week. There we have shown something like this. So I am repeating that idea. If you if you have seen that question I have solved in either week 2, week 3 or week 4. I am not remembering exactly in which tutorial session, but we have used this kind of trick previously also. So now our aim is to find to show 2a, this is some integer which is rather different from a, and this 2a belongs to this set. This is the main problem here. So once we can show this statement, then we are done, because this is the logic behind that. Now so we can write it as enough to show that 2a belongs to this set, enough to show 2a belongs to this set, because then we will have 2a times a, that means 2a square, this divides n minus 2 factorial. Now 2a square means 2n, so then we can conclude n divides 2n and 2n divides n minus 2, so in that way we will get a contradiction. Now here we show why 2a will belongs to the set 3 up to this. Now what is the condition given? We have considered a is greater equals to 3. This is one condition, and another condition was a was greater than 3. Now 2a belongs to this set, so obviously that will imply 2a, this is also greater equals to 3 or greater than 3, strictly greater than 3. Now so it is equivalent to show this one, it is equivalent to show. So we have got the lower bound, only we have to show the upper bound. That means we have to show 2a, this is less than, strictly less than, or not strictly less than, or you can say less equals to n minus 2. If 2a belongs to this set, this is equivalent to show 2a is less equals to minus 1. Now this condition, this is equivalent to n minus 2a minus 2, this is less equals to greater equals to 0, say. Now n was a square, that means n was a square, so this is equivalent condition. Now this is equivalent to this. Now a was now so to show this one, it is equivalent to show this one. So can we show a times a minus 2 minus 2, that is greater equals to 0. Now we have, this is just calculation, I have checked, I don't know, there may be some another way to show this kind of question, but this is the way I have solved. So given condition was a greater equals to 3. Therefore what we can conclude, so it was a times a minus 2 greater equals to 2. So we can check a times a minus 2, since a is greater equals to 3, this term will also be greater equals to 3, and this will imply a into a minus 2, this term is minus 2 greater equals to 1, that means this is greater than 0. Thus, so since we are getting this conclusion from the given condition a greater equals to 3, from here we can go here, then here, then here, then here, this, because this, and then here. I mean, this is actually if and only if condition, right? So, and it is equivalent, therefore the what we got, thus 2a belongs to 3 up to n minus 2, and hence a not equals to 2a with 2a square divides n minus 2 factorial. Okay. So I think I have the way I have done it is little bit complicated, because there are too many cases. First case, what we have shown n is a composite number such that n equals to a times b with a not equals to b. In this case we are done. Then we have considered another case where a equals to b, that means n is a perfect square. Now to show some contradiction to our main hypothesis, what we have done, we have considered, we have break that case 2 condition, that means when n is a perfect square, in two terms, in two cases again, two sub cases. So first case was the trivial case, when we are considering a to be exactly 2, that means n equals to 2 square, that is 4. In that case we are getting that n minus 2 factorial, this is not congruent to 1 mod 4, that is mod n. So n cannot be 4. Now we are considering n is a perfect square when a is greater equals to 3. In this case what we have shown, we are trying to show n minus 2 factorial that will be divisible by n. So now n has the form a square. So if n divides n minus 2 factorial, what we have to show? A square is dividing n minus 2 factorial. Now we know a is a term which occurs in the set 2 up to n minus 2. So to show that a square will also divide n minus 2 factorial, we need to find some another integer, like here we have shown that integer is exactly 2a, such that 2a also lies in the set 2 up to n minus 2. So this is the thing we have shown, we have shown in this way. This is the proof where we have shown that 2a will also lie in the set 3 up to n minus 2. So if once we have shown 2a belongs to this set, what we are getting? We are getting a times 2a that occurs in the multiplication 2 into 3 into 4 up to n minus 2. That means a into 2a, that means 2a square divides n minus 2 factorial, and hence n square will also divide a square will also divide n minus 2 factorial. Then we are getting the contradiction to the hypothesis that n minus 2 factorial congruent to 1 mod n. So thus we have shown for the case where n is a perfect square. Now there is something there is some trick I have applied in this proof to show 2a belongs to this set. What is that trick? We have considered the equivalent conditions of saying 2a lies in this set 3 up to n minus 2. Now since a greater equals to 3, this subcase we were considering, so a greater equals to 3, that will give us 2a will also greater than 3. This is the lower bound. So we have seen that 2a greater equals to 3 means another bound we have to show is the upper bound. That means 2a is less equals to n minus 2. So to show that n minus 2 is the upper bound of 2a, we have break it in the equivalent conditions. It is 2a is less equals to n minus 2. It is equivalent to say n minus 2a minus 2. This is greater equals to 0. This is equivalent to say this condition. This is equivalent to say this condition. That means a into a minus 2 minus 2 greater equals to 0. Now since a greater equals to 3, so from here if we multiply some another positive integer with a, that will give us some integer greater equals to 3. So since a was greater equals to 3, if we multiply some another positive integer, this product will also be greater equals to 3. Now from here we conclude this is greater equals to 0, which is this equivalent condition. Thus we get the upper bound of 2a, which is n minus 2, and hence we have shown that 3 less equals to 2a less equals to n minus 2. Hence 2a lies in this set. So this is the trick or calculation you may say I have applied to show that 2a will be another integer different from a, which occurs in the factorial n minus 2. So in that way we show our main hypothesis. So hence the 2a square divides n minus 2, that implies n divides 2a square divides n minus 2 factorial, implies n minus 2 factorial congruent to 0 mod n, and hence this is a contradiction to the hypothesis. Thus n cannot be a composite number. So this question has too many cases, so be careful and go through once again with the proof if you don't understand. Now let's so these were the problems I have chosen which has the application of Fermat's theorem and Wilson's theorem. Now do some, okay, it's already 4:44, so quickly we will see 2 or 3 questions, and I have to give you one homework, I mean you have to do yourself. So let's go to the another topic, which is Euler's phi function. So it will be question number 4. First question is, if n is odd, then what was the phi function? First recall. What was the phi of n for an integer n? This was, what was phi n?
Ma'am, this is a counting of integers less than n
And
whose GCD with n is 1.
so this consists of, okay, how to write it? 0 less, not 0. Such that GCD of an equals to 1. Right? Now there are some formula. If let's say n equals to p power e, then what was phi of n? Tell me quickly.
P power e minus p power e minus 1.
And if n, okay, so what will be, this was another thing, and what it will be, phi of a times b, that when GCD of ab equals to 1, what was that?
Phi a into phi b.
Phi b. And if n has the prime decomposition p1 power alpha 1 up to pk power alpha k, so then what will be phi n? What was the form of phi n?
That will be n times 1 minus 1 over p1, 1 minus 1 over p2, and so on.
Up to,
1 minus 1 over pk.
right? So these are the theorems we have and definitions we have seen in the lectures, and now let's try this question number 4. So it is saying, if n is odd, then, okay, it is homework. I mean, I will solve the next one, then it will be given you as homework, then so that phi of 2n, this is exactly phi of n. This is homework, you can say. And now let's solve this one. If n is even, then so that phi of 2n, this is equals to 2 phi n. So the theorems I have recalled, using those things actually we will show this question number 5. So can you try to solve this one? So I am giving you the hint, use the prime decomposition formula for phi n. So further I can show you, give you this one. Let's take n equals to p1 power alpha 1 up to pk power alpha k. So can you tell me something, when n is even, can you have some particular form of prime decomposition of n? N is even, what does it mean?
It will be multiple of 2.
Multiple of 2. So in prime decomposition, what can we say? The power of 2 will be non-zero.
Yes, yes, ma'am.
So
At least 1.
at least 1. So since n is even, write the prime decomposition of n in this form also, where n equals to 2 power r into p1 power alpha 1 up to pk power alpha k, where the pi's are different primes from 2, right? Since so why can we write this form? We can write this as n is even. Now where 2 not equals to pi for all I equals to 1 up to k, right? So from here what can you conclude? Phi of, so what will be 2n then? 2n will be power of 2 will raise by 1, 2 power r plus 1, and p1 power alpha 1 up to pk power alpha k, because 2 is 2 not equals to any pi, therefore 2n will have this prime decomposition, and from here we can say phi of 2n equals to n times, that means 2 power 2n times 1 minus half 1 minus 1 by p1 up to 1 minus 1 by pk, this. So what was the prime decomposition of, what is the difference between prime decomposition of n and prime decomposition of 2n? Just there is one extra 2 in that 2n, so if you take 2 outside, n times 1 minus half 1 minus 1 by p1 up to 1 minus 1 by pk, what this term gives you? What is this term?
That will be phi n.
Exactly phi n. Thus we have shown phi of 2n equals to 2 phi n. So using this concept you can answer this question number 4 also. Now let's solve another one similar kind of question, question number 4, 5, 6. 3 so that uh, 3 divides n if and only if phi of 3n, this is equals to 3 phi n. So can you try this problem? At least one direction, can you tell me? In a similar way you can show this one, considering the prime factorization of n. So first consider this direction, that means let 3 divides n. Then from this condition what can you say how the prime decomposition of n will look like?
Now we can say n is equal to 3 times some integer k, and
3 times k. So
we-
in terms of prime decomposition, what can you say?
it's a multiple of 3, and
It's okay, it's multiple of 3, but in terms of prime decomposition I am asking, like the previous question what we have seen.
like it will be 3 raised to power something.
So
And
power of
one-
3 will be non-zero here,
Yes ma'am, at least 1 will be
at
there.
least 1. So let's consider 3 power r, this is the power of 3 in n. Then there will exist some other primes, p1 power a1 up to pk power ak, where not equals to pi for all I equals to 1 up to k. So this is the given condition. So again phi, what will be phi of 3n then? So first, what is 3n? 3n is 3 power r plus 1 p1 power a1. The remaining powers of pi's will not change because 3 is none of those pi's. So ak, that will imply phi of 3n, this is equals to 3n times 1 minus 1 by 3 into 1 minus 1 by p1 up to 1 minus 1 by pk. Now same way, take 3 outside, then it is 3 n into 1 minus 1 by 3 into 1 minus 1 by p1 up to 1 minus 1 by pk. So it will, the term inside this third bracket, it will give you phi n. Thus we have shown phi of 3n equals to 3 phi n. So this is one direction, but the condition is if and only if condition. So remaining case is to show the reverse direction. So that means what we have to show, considering phi let phi 3n equals to 3 phi n, want to show 3 divides n. So what will be what should be the approach to show, I mean in how many ways we can show that 3 divides n? Either we have to show that n equals to 3k for some integer k, or we can show the by the method of contradiction, right? So let's 3 divide n, how can we show that power of 3 in the prime decomposition, that is non-zero. That is also one way to show, but here we can so considering prime decomposition of n, then showing that p1 will be 3 for pi will be 3 for some I from 1 up to that k, that means in the prime decomposition of n. This is one way, but for that, okay, let's try that way. If we don't get, then we will use the method of contradiction. So first let, but I think that will be difficult to show only from this condition. It will be difficult to show that 3 is one of the prime in the prime decomposition. So my suggestion is to consider to use the method of contradiction. This is what I am expecting to. Okay, let's use that. Let us use the method of contradiction. So to use the method of contradiction, what we have to show. So assume 3 does not divide n. 3 does not divide n means if we consider any prime decomposition of n, the primes that occurred in the prime decomposition of n will not be 3. So assume 3 does not divide n, then we somehow we have to show the contradiction to this fact. Okay, so if n does not divide 3 does not divide n, then consider the prime decomposition of n to be p1 power alpha 1, p2 power alpha 2 up to pk power alpha k, where pi not equals to 3 for all I equals to 1 to up to k. So then in this case what will be 3n? In this case what will be 3n? Just 3 power 1 into p1 power k1, p1 power a1, right, or alpha 1, p1 power alpha 1, p2 power alpha 2 up to pk power alpha k. Since none of those pi's from p1 up to k 3 not equals to those pi's, therefore 3n will have this prime decomposition. So in from here what will be phi of 3n? What will be phi of 3n here? Tell me quickly. From this prime decomposition what can you say? Phi of 3n? Just follow the definition. Tell me, anyone?
That can be 2 times phi of n.
So just tell me step by step. Don't step jump.
Because all things are co-prime. Phi of 3 into phi of pi's, all the pi's.
Phi of 3 into phi of...
Phi.
Okay, this way also is correct.
Then phi of 3 will be 2, and similarly we can
So
have 1.
this is phi of 3, 2, and then phi of... That means this is exactly phi of n, right? This term?
Yes.
This term is exactly phi of n. So you will get this phi of 3n equals to phi of 2n. But in our hypothesis what we have assumed? We have assumed phi of 3n equals to 3 phi of n. But here assuming that 3 does not divide n, we are getting phi of 3n equals to 2 phi of n, which is a contradiction. Hence 3 divides n. So can you say can you have some conclusion from, I mean, if I ask what will be the if and only if condition? Okay, so this is question. So 3 does not divide n. This is equivalent to, say, can you tell this one? Phi of 3n equals to 2 phi n. Can you show this one? Just one direction we have exactly shown here in this reverse statement. To show the reverse statement, we have actually shown this direction. So just another direction we have to show that if phi of 3n equals to 2 phi n, we have to show 3 does not divide n, and this is the thing you can show by yourself easily. And this is the last question I would like to solve, and it is something easy, and after that we will stop. It will take only 2 or 3 minutes maximum. Let n greater than 1 has r distinct prime factor, then so that phi of n, this is greater equals to n by 2 power r. Okay. So can you just show it by using the same formula we are using so far, that I mean by considering the prime decomposition of n. So n is greater than 1 and n has r distinct prime factor. That means what will be the prime decomposition of n? It will have this kind of form: p1 power a1 into p2 power a2 up to pr power ar. Since n has r distinct prime factors, we can write the prime decomposition of n in this way. Okay. So from here, what can you say? Phi n? Phi n equals to so also another thing is given, n is greater than 1. So n is greater than 1, that means so this condition also you have to use. So can you tell me?
Ma'am, can we show something like that? First of all, phi of n will be n times 1 minus 1 over p1 and so on. And we can observe here that 1 minus 1 over pi is always greater than 1 by 2. And then
So phi n has this form. So you are saying to show 1 by
1 minus 1 by pn p1
that is 1 each element.
pl
Yeah,
yes,
pi.
PL.
This is
Always be greater than is equals to 1 by 2.
so yeah, that why is that?
Ma'am, because for the smallest prime 2, then after that it will be greater than.
After that it will be, since n is greater than 1, so the least p it can be, that is 2. So see, now we have pi greater equals to 2 for each I.
Yes, yes.
So that will imply 1 upon pi less equals to minus so less equals to 2. That means if you take minus, so it will give you
1 by
1 minus 1 by pi greater equals to 1, sorry, this is 1 by 2, this is 1 minus 1 by 2, that is half. So thus we have, this is for all I equals to 1 up to k, oh sorry, r up to r. So thus 1 minus 1 by p1 up to 1 minus 1 by pr, this product is greater equals to half times up to half. How many times? R times. So thus phi of n, this is greater equals to, so this is equals to 2 power r. So phi of n greater, phi of n was this term multiplied with n. So thus phi of n will be greater equals to n upon 2 power r. So can you tell me when the equality occurs? Here this is inequality. When the equality occurs?
Then when you take n2, then it will
N is 2, that 2 or power of 2? not only 2, if n is power of 2, then we will get the equality. That means n equals to 2 power some a. So these are the questions I have prepared for today's lecture. So anyone has any doubt what we have done so far? So if not, shall we stop here? So let's stop here today, and bye bye.
Thank you, ma'am.